waste of time. Okay. This is what we discussed on Tuesday. We're looking at the limits. We spoke of the one-sided limit and also the two-sided limit. And the main thing that we learned from this is that for a two-sided limit to exist, both the one-sided limits must exist and they should also be equal. So if the two-sided limits exist but are not equal, then we end up saying that the two-sided limit does not exist. So if we use this diagram which I drew explaining something to one of you who asked me a question as to regarding why do we have a solid dot here and we have just a small circle up there to indicate that we are talking of intervals. So if, for instance, we talk of the limit of our function f of x as x approaches, say, 2 from the left, and we also look at the limit of f of x as x approach 2 from the right, then we will observe that when we talk of the limit of f of x when x is approaching 2 from the left, this is what we have, and then the result will be a 2 from the graph. And when we approach 2 from the right, we'll be moving like this. Then we check as to what is happening on this graph. We'll be moving towards the output, which is a 3. That's what we are talking about. And therefore, when we compare the two, we realize that the limit of f of x when x is approaching 2 from the left is not equal to the limit of f of x when x is approaching 2 from the right. And once we have that, then we conclude that therefore we can say that the limit of f of x when x is approaching 2 does not exist. That's what we discussed previously. So for today, we can start today by looking at this example where they are saying sketch the graph of f defined piecewise like this, and use this graph to find the limit of f of x when x is approaching 1 from the left, the limit of f of x when x is approaching 1 from the right, and the limit of f of x when x is approaching 1. That's what we are interested in. So if we draw the graph, this is what we have. Sorry. Let me use the black color. This is what we have, the axis. And then the first one, this equation is just like saying we want to draw the graph of y equal to 3 minus x. And we will observe that when x is 0, y will be 3. So if I decide to put a 3 here, then that is the y-intercept. And when y is 0, x again will be a 3. So if we put 3 there, then it will be a line going all the way like that. But it is given by 3 minus x only for values of x which are less than 1. So if we put, say, 1 here, and another 1 here, and a 2 here, this is 1. Let me say this is a 3. Then a 2 will appear in between here. So we are interested in y equal to 3 minus x for values of x which are less than 1. 1 is here. So we will be interested in values of x on the left-hand side of 1. So the graph will look like this. This is a straight line going like that. Then they say we also have y equal to 1 when x equal to 1. So when x equal to 1, y will be 1. So this is just a point there. And furthermore, they say we have y equal to 2 plus the square root of x minus 1. So what we know is that if we were to draw the graph of y equal to square root of x, this will just be a graph going like that. So it's the positive part of x equal to y squared. If we look at x equal to y squared, it has a positive and negative part. Bottom one will be the negative one. So we have that. So in this case, we are shifting this to the right by 1 unit. So shift to the right by 1 unit, it will be like this. Then when we add a 2, it is like moving this graph up 2 units. So here we have a 2, and then we moved it 2 units up. It's a graph going like that. Okay, so if we look at the limit of f of x, when x is approaching 1, from the right-hand side, it means we are moving like this. We're getting closer and closer to 1. From the right-hand side, we will be moving along this curve. So the output there is a 2. Similarly, if we talk of the limit of f of x, when x is approaching 1 from the left, we'll be moving like this towards 1. Then we'll be moving along this straight line. Then the output again is 2. Therefore, we can see that the left-hand limit and the right-hand limit both exist, and they're equal to 2. And because they are equal, then we can conclude that the limit of our function f of x when x is approaching 1, it's a 2. That's what we have. So here, I just want us to revise or to look at the limit laws. They're important because sometimes we ask you to apply them when you are dealing with these limits so that the logic is clear. I understand that okay. So the limit laws go like this. Suppose that C is a constant. In other words, it's just any real number. And then the limits, say, limit of f of x when x is approaching a exist, and the limit of g of x when x is approaching a also exists. So we are just using 2 functions here, y equal to f of x and y equal to g of x. You can talk of more than 2 functions. It doesn't really matter, but 2 will be enough to illustrate the laws. So the first law is that if you are evaluating the limit when you are approaching A, you have your function f of x added to the function g of x. The result will be the same thing as evaluating the limit using f of x when x is approaching A, then adding to the result that you are going to get after evaluating the limit of g of x when x is approaching A. So either you can start by adding the two functions together, or you can evaluate each limit separately and then you add them. Similarly, for subtraction, you can first find the difference between the two functions, then evaluate the limit, or you find the limit of your first function as x approach A, then the limit of g of x when x is approaching A, then you find the difference. Then this difference will be the same as that difference you are going to get there. Okay. So if you have C, which is a constant, multiplying your function like that, and you evaluate the limit, it is the same thing as putting C to the left-hand side of the limit, then you evaluate your limit, then getting this result, multiplying it by this C, then the result will still be the same as what you got on the left-hand side here. And furthermore, we are saying that the same goes for the product. We have two functions, the product of two functions. You can evaluate the limit for the first function, the limit for the second function, then you multiply the result together. And we also have the quotient, goes like that. I think it's natural that if you have a quotient of two functions like this, and then the limit of this quotient is the same thing as finding the limit of f of x, then you divide by the limit of g of x as x approach A. And of course, we make sure that the limit of g of x as x approach A is not equal to 0. This should have started on a new line where we are just saying that if, say, for argument's sake, you look at number 4, we've got two different functions. But here we are explaining the fact that we can have the limit of a function multiplied by itself and so on, because if you have f of x raised to the exponent of n, is just f of x times f of x times f of x times f of x to the n power, like that. So we are saying that if we use the product law repeatedly with the g of x equal to f of x, we obtain the following law. So you have f of x raised to the exponent of n, you are evaluating the limit as x is approaching A. This will be the same thing as evaluating the limit of f of x as x approach A. And after getting that limit, you raise it to the exponent of n, where n is a positive integer, like that. And then we are saying that it is also important for us to understand that the limit of a constant when x is approaching A is just that constant, and the limit of x when x is approaching A is just A. So now, direct substitution property, this is something you are used to. When do we say the limit of f of x is as x approach A is just f of A? When do we say that? So we are saying here that if f is a polynomial or a rational function, if it is a polynomial or a rational function, and the A is in the domain of F. That's very important. That's the thing that we check, because you check whether f of x is a polynomial or a rational function. If it is, then you check whether A is in the domain of the function. If that is the case, then to evaluate the limit, you just take the number, you replace x with it, and you will get the result. But don't forget that when we evaluate the limit, we are not interested in what happens when x equal to a. We are interested in what happens to our output when x is very close to a. That is very important. So functions with direct substitution property are called continuous. So these are continuous functions which are easy to work with. We will define continuity later. And then they are continuous at A and will be studied in more detail later. However, not all limits can be evaluated by direct substitution. That is another important point. So if we take this example, if we look at this example, they say find the limit, and then they give us x squared minus 3 over x minus square root of 3 when x is approaching square root of 3. Then the question that we will ask ourselves is whether this square root of 3 is in the domain of this function or not. Then you will observe quickly that if x is equal to square root of 3, then we will be forced to divide by 0. In fact, it will be 0 over 0, which is indeterminate. It does not make sense, okay? Because square root of 3 is not in the domain of f of x. So what we are going to do is to find another function whose limit will be the same as the limit of this function when x is approaching 3. Because again, the important thing is we will not be interested in what happens when x equal to square root of 3, but what happens when x is very close to square root of 3. So we find another function whose limit does exist when x is approaching square root of 3. And that limit will be the same as the limit of this function that we're talking about here. So to do that, we just modify what we have like this. So as a solution, we can say that the limit of our function x squared minus 3 over x minus square root of 3 when x is approaching square root of 3. There are many ways of dealing with this. The first one is we can factorize x approach square root of 3. Then we are looking for another function equivalent to this one. So if we factorize the numerator, we have x minus square root of 3. This is difference of two squares. X plus square root of 3. Divide this by x minus square root of 3. Like that. And then we can see that this and that will cancel out. Then we're left with the limit of x. X is approaching square root of 3. X is approaching square root of 3. X is approaching square root of 3 of what function now? We have x plus square root of 3. So we started off with this function. Then we have another function whose limit will be the same as that one when x is very close to 3. Okay, so we note that this square root of 3 is in the domain of this new function. Square root of 3 is in the domain of this new function. So this is giving us square root of 3 plus square root of 3, which is 2 square root of 3, like that. So what we have just done is explained here that we compute the limit, or we computed the limit above by replacing the given function f of x equal to x squared minus square root of 3 over x minus square root of 3 with a simpler function g of x equal to x plus square root of 3, which has the same limit as the original function. This is valid because f of x equal to g of x except when x is equal to square root of 3. And in computing a limit as x approaches 3, we don't consider what happens when x is actually equal to square root of 3. So maybe before we move on, let us go back to this question. And I said there are many ways. Let me also take this opportunity to indicate that one can also approach the very same problem like this. The limit x is approaching square root of 3. You have your x squared minus 3 over x minus square root of 3. This is equal to the limit x is approaching square root of 3. X squared minus 3 over x minus square root of 3. We multiply by 1, or we rationalize the denominator. So we have x plus square root of 3 over x plus square root of 3. So this is 1. Okay, so if we do that, then it tells us that we are going to have the limit x is approaching square root of 3 of x squared minus 3 into x plus square root of 3 divided by this product. We are just reversing difference of two squares. So we have x squared minus 3, which is the same as that. So we end up with the limit x is approaching square root of 3 of x plus square root of 3. And then now square root of 3 is in the domain of our new function g of x, and we end up with square root of 3 plus square root of 3, which is 2 square root of 3, like that. So you can either factorize, or you multiply by 1. You multiply by 1, but this 1 is guided by what we have here. So kind of we say we are rationalizing the denominator. Yes. So we've already explained what is happening. So what is important for you to note is that we are saying if f of x equal to g of x when x is not equal to a, then the limit of f of x when x approach a equal to the limit of g of x when x is approaching a, provided the limits exist. So if both the limits exist, then we make this conclusion. That is why we were able to do what we did up there. So here we are also emphasizing the fact that the limit of f of x when x approach a is not always equal to f of a. It's not always equal to f of a. Because sometimes you will think that to evaluate the limit of f of x, you just take a, you put it where there is x, and then you get the answer. It is not always true. Let us look at this example. In this example, we are given g of x, which is piecewise defined like this: g of x equal to x plus 1 when x is not equal to 1, and g of x equal to pi if x equal to 1. So you will note that if we talk of the limit of g of x, when x is approaching, it can approach 1, either from the left or from the right, it doesn't really matter. But the way the function has been given, x is approaching 1, the way the function has been given, we are saying g of x when x is not equal to 1. So when we are evaluating the limit, we should understand that we are interested in a situation where x is not equal to a. So in this case, we will be interested in a case where x is not equal to 1 because we are approaching 1, we are not at 1. So this will give us x plus 1 like that is our function, and this limit is going to be 1 plus 1, which is a 2. And if we look at g of 1, when x equal to 1, g will be pi. And we note that the limit of does not want to move, but nevertheless, it's fine. But the main thing, the thing that I want you to note is this. Let me put it up here. You must note it's important for us to understand this. You must note that the limit of g of x when x approach 1, in this case, is not equal to g of 1. It's not equal to g of 1. It's not equal to g of 1. That's the thing that I want you to observe, that the limit of g of x is not equal to g of 1. That's very important. The g of 1 is pi, but the limit of g of x when x approach 1 is equal to 2. So you don't necessarily say, I will substitute 1, take x to be equal to 1, then I will get the correct answer. Okay, I hope that is okay. Then the next example, we just want to look at this kind of limit. We have a rational function. Again, the first question that we ask ourselves is that is 2 in the domain of our function? We ask whether 2 is in the domain of this function. And of course, if you know what a domain of a function is, you will observe that 2 is not in the domain of this function, because if you take 2, you put it where there is x, then you have 2 squared. 2 squared minus 4 is 0. So we are forced to divide by 0. Therefore, we have a problem. So 2 is not in the domain of this function. And because very well, if maybe you talk of limit laws, you try to find the limit of the top over the limit of that one, then you will be, if you try to use number 5, if you just go straight away, then you will have a problem here, because in this case, the limit of the denominator is equal to 0. So before we do this, we must be sure that the limit of the denominator is not vanishing. It is not equal to 0. So in this case, we observe that the limit of x squared minus 4 is 0. So we don't do it that way. So how do we do that? We can look at our function in this way. We have the limit. X is approaching true. This can be factorized. Is x minus 2 multiplied by x minus 2. Denominator can be factorized x minus 2 x plus 2. So we end up with the limit. X is approaching true. This and that gone. So we have x minus 2 over x plus 2, like that. And then we check, is 2 in the domain of the denominator? Yes. Is 2 in the denominator of the domain of the numerator? Yes. So we can do direct substitution, which is 2 minus 2 over 2 plus 2, and that is a 0, or 0 over 4, which is a 0, like that. So, but for this one, if you want, you can first do the division, use long division, and write this as a new fraction, but it's okay to factorize like that. Now, again, this one I think is in the same class, because we have x is approaching 2, x minus 2 over x minus 2 into x plus 2. This and that gone. So we have the limit of 1 over x plus 2 when x is approaching 2, like that, which is 1 over 2 plus 2, which is 1 over 4. Straightforward. Yes. Now, let us look at number C. Let us look at number C. With number C, I think okay, we are talking of the limit of x minus 3 over x squared minus 4 when x is approaching 2 from the right. It is approaching 2 from the right. So what we need to observe in this case, because if you compare this number C with, say, number A here, number A, you will know that in number A, when you take the 2, you put it where there is x, you get 0 over 0. 0 over 0. Okay, that's important. And when we got this 0 over 0, we realize that the limit does exist. It's equal to 0 in this case. But now in this one, you will note that if you take your 2, 2 is not in the domain of x squared minus 4. In fact, well, should I say that it is in the domain of x squared minus 4, because x squared minus 4 will be a 0. You take the 2, you put it here, you have 2 minus 3. You see? But this is 0, so it is reminding us of law number 5. Law number 5. In this case, our denominator is 0, so we cannot just do direct substitution like that. You cannot just do direct substitution like that. So basically what I want you to note is that in this case, if x is approaching 2 from the right, it simply means that we are using values of x which are bigger than 2. Values of x are bigger than 2, because if we look at a number line like this, and then we have a 2 here, when we are getting closer and closer to 2 from the right, these numbers are bigger than 2. So if you take a number which is bigger than 2, you square it, you'll get something bigger than a 4. Okay, you get something bigger than a 4, which is positive. And then you have that number, it's very close to 2, but it is less than 3. So that number, because it is small, you subtract 3, you get something which is negative. So you have negative over something which is positive. But when we are getting closer and closer to 2, this is getting closer and closer to 0. X squared minus 4 is getting closer and closer to 0. But what we are interested in is what kind of a number which is getting closer and closer to 0. Is it positive? Is it negative? Here it is a positive number. Here we have a negative number. That's why in this case we will say the limit here it's minus infinity, because this is giving us something which is negative, this is positive, so we have minus infinity. So the main thing here, maybe I will explain the reason why we're using this example a little bit later. Let us look at number D. Let us look at number D. If you look at number D, it's the same as this one, because for number D, if you look at the number line, if your 2 is here, you will be getting closer and closer to 2 from this side. Remember, we are not interested in what happens when x equals 2, but what happens when x is very close to 2. So if we take a number which is less than a 2, when you square that number, you get something less than a 4. And then a number which is less than 2, you subtract 3 from it, you get something negative. So it's negative over negative, and you end up with a positive infinity. So note that for number C and number D, we are not just saying the limit does not exist. We are using these symbols, even though, yes, infinity is not necessarily a number, but it shows us that in this case, this limit, the value is a very large negative number, which we do not know. And this one, it's a very large positive number, which we do not know for number D. Therefore, for number E, we could see that the left-hand limit and the right-hand limit, because these two together should give us this one. They should give us this one. So basically, the limit, when we are approaching 2, in this case, we can say does not exist. Why are we saying that? Because for the limit to exist, we must have the left-hand limit and the right-hand limit. They should both exist and they should be equal. So we cannot talk of, you cannot say negative infinity is equal to positive infinity. They are not equal. All right. So that is the importance of this example. Lastly, is it lastly? Yeah. Lastly, let us look at these 3 examples. Let us look at these 3 examples. The first one here, they say evaluate the limit. H is approaching 0 with 3 plus h squared minus 9 over h. Like that. And then we note that 0 is not in the domain of our denominator or of this function, because when we put 0 here, then the denominator is 0. Even the numerator is 0. But the beauty of this is that if we get 0 here and we get 0 on top, this numerator, we know that the limit does exist. We know that it does exist. But if you look at this, the last example that we did here, this one, number E, when you try to do direct substitution, if you put 2 here, you get -1. And down here you have a 0. So we don't have 0 over 0. Then quickly we conclude that the limit does not exist, because we have a non-zero real number and a 0 when you do direct substitution. So it's a non-zero real number divided by 0, which you cannot remove in any way whatsoever. So that's why we say the limit does not exist. But in this case, the limit does exist because we have 0 over 0 from direct substitution. So this is going to be equal to the limit h is approaching 0. Then let us rewrite this. This is 9 plus 6h plus h squared minus 9 over h, like that, which is the limit. H is approaching 0. 9 minus 9 is 0, so we've got 6h plus h squared over h. H is common, so we have the limit of h into 6 plus h over h. H is approaching 0. This is just the limit of 6 plus h when h is approaching 0, like this. And when we substitute the 0, we get a 6. Similarly, for number 2, you have the limit x is approaching 0, square root of x squared plus 100 minus 10 divided by x squared, like that. So 0 give us 0 here. 0 square root of 100 is 10. 10 minus 10 is 0. So this is giving us 0 over 0 when we are looking at the law number 5. Therefore, the limit does exist. So what we are going to do is multiply this by 1. We rationalize. We have plus 100 plus 10 divided by square root of x squared plus 100 plus 10. And after doing that, then we end up with the limit. X is approaching 0, difference of 2 squares. So this is x squared, x squared. So we end up with x squared plus 100 minus 100. 10 times 10, it's 100. Square root of x squared plus 100 times square root of x squared plus 100 is x squared plus 100. Divide all these things by x squared into the square root of x squared plus 100 plus 10. This is giving us the limit of x squared when x is approaching 0 of x squared square root of x squared plus 100 plus 10. It's x squared and x squared gone. So we end up with the limit. X is approaching 0 of 1 over square root of x squared plus 100 plus 10. And then when we put 0 here, we've got 1 over square root of 100 is 10. 10 plus 10 is 2 times 10, which is 20. Like that. And note, the way I am writing, you can see I'm writing equal signs in the right place, and we have the limit appearing throughout. So make sure you do likewise. And I just want to do this one for you, then we call it a day. Let us quickly do number 3. Let's quickly do number 3. Number 3, we are looking at the limit x is approaching 0 of 1 over x square root of 1 plus x minus 1 over x, like that. Now, the first thing that we need to do, if we think in terms of our limit laws, it means we will talk of the limit of the first function as x is approaching 0 and the limit of 1 over x as x approaches 0. So for the first one, you will have 1 over 0. Okay. The second one, it's 1 over 0. Okay. So 1 over, it's like 1 over 0. Let me use another color. This is not what we first erase this. I'm saying if we're applying the limit laws, we'll have 1 over 0 here, minus 1 over 0. So we end up with, okay, I was saying 1 over 0 minus 1 over 0, which is like infinity minus infinity. So if we ask you, what is infinity minus infinity? What would you say? What is infinity minus infinity? Just that I muted you, but what do you think infinity minus infinity is? Of course, some of you may think it is 0. It is not. It is not 0. It is not 0. But the point here is, when we get this kind of a situation, infinity minus infinity, we know that the limit does exist. We know that it does exist. Just like when we get 0 over 0 up there, we knew that the limit does exist. So what we're going to do is just to rewrite this algebraically. We have this, you know how to add two fractions. We speak of the lowest common multiple of the denominators, LCM, between x square root of 1 plus x and x. The LCM here is just x square root of 1 plus x. So x square root of 1 plus x. Then we divide this into that. We get a 1. 1 times 1 is 1. Then we divide x into this. We get square root of 1 plus x, and times that it will be minus square root of 1 plus x, like that. And once we do that, we note that we still have 0 over 0. It's still giving us 0 over 0. So let us rationalize or multiply by 1. 1 minus square root of 1 plus x divided by x square root of 1 plus x multiplied by 1 plus square root of 1 plus x. Divide this by 1 plus square root of 1 plus x. This is giving us the limit. X is approaching 0. The top will be 1 minus x when we remove the brackets. And this is over x square root of 1 plus x into 1 plus square root of 1 plus x, like that. 1 minus 1 is 0. That x and x will cancel. So we're left with the limit. X is approaching 0. 1 gone. This cancel with that. So we're left with minus 1 over square root of 1 plus x into 1 plus square root of 1 plus x, like that. And then now we can do the substitution. Then we end up with minus 1 over, if we put 0 here, you have square root of 1, which is 1. You put 0 here, you have square root of 1, which is 1. 1 plus 1 is 2. There you are. And then I encourage you to look at the exercises on page 18 and 19 on our pamphlet. You look at exercise 46, you can do 1 up to 27. And then if you do that, then you will have a good foundation on which we are going to build. You will have a good foundation. Okay. Okay, I could see we have Rothuang down raising a hand, Ratilwe Wikanyo, and Masindi Ramboa. Rothiwa?
Sorry?
Like, this is noise. This is noise.
Hello?
Yes, if you have a question.
As I was saying, I didn't understand. You said that you had
There is background interference in your where you are. I can't hear, we cannot hear you properly. There is noise. We can't hear you.
Hello?
Yes, maybe you are clear.
Yeah, you're speaking to Ropiwa. So I wanted to ask, sir.
Yes,
I'm
yes.
not like, I didn't understand the part where, like you said, like where I didn't understand the factorization part for x squared minus 3, where you open two brackets and the one has x minus root 3 and the other one has x plus root 3. I didn't understand where that root came from.
We are factorizing x squared minus 3.
Yes, I didn't understand the first part. Yeah, where you said x minus root 3 close brackets, then x plus root 3 over x minus root 3. I didn't.
Okay, let me ask you so that we help each other. And
Yes.
let me write something here. Let me use this color. I'm writing here. You can see that I'm writing, right?
Yes.
So if say for argument's sake, you have, they say factorize x minus 4. Do you know how to factorize this?
Yes, I do.
What are the factors? It will be x minus
2 and x plus 2.
Plus 2. Okay?
Yes.
Good. So how did you get the 2? These 2?
I got them. I got them from -4.
You get the 2 from -4.
Yes.
How?
Oh.
Because that's what we are interested in the how, the why of things. Because now here you have x squared minus
Yes, I
minus
understood.
3.
I understood, sir.
You see now
Yes,
where
I see.
the square root of 3 comes from.
Yes, I see. The problem is that I add instead of multiplication. I used addition instead of multiplication.
Addition, I don't understand now.
Yeah, that was the problem. So like now I understood. Thank you, sir.
Okay. Thank you very much. Thank you very
The
much.
topic for the quiz.
Thank you very much.
Hello, sir.
Yeah, we have more questions on what we were discussing.
Hello, sir.
Where
Yes.
can we get them?
I have the problem on rationalizing the.
Okay.
Yeah.
Let us look at it. Let us. Okay. Even in this one, we rationalized. Okay.
Yeah.
Yeah. What we do. So basically, you see, we want to get rid of the radical sign, the square root. Okay, we looked at the denominator, which have got a square root, right?
Okay.
And then what we do is just, we call this a conjugate. I think in your language, we call it a conjugate, not necessarily a modulus, but sometimes we speak of modulus and stuff like that. That if you have a number given like this, then you can change the sign. See, we have x minus 3 this side, and then we change the sign, it is positive. But this is it's a 1. You know very well that if you take a real number, you multiply by 1, it remains the same, not so.
Yeah.
So remember, this is just a number. We're just saying having a number, another number. And then we took the denominator and we wrote it like this. We're guided by what we have here. If it was a plus here, we would put a different sign. It will be negative there. But again, this is 1. So that's how we do the rationalization. And the moment we do that, you can, if you look at the numerator, it will be this expression multiplied by that expression. This is what we have. In the denominator, you will see quickly, this is like you have factored the difference of 2 squares. This difference of 2 squares, x times x squared, the middle term is 0. Square root of 3 times square root of 3 is 3, like that. So it is the same thing as, okay. Yeah, I wanted to say it's the same thing as what we did here.
Okay. Yeah, but here you didn't check the denominator.
Yes,
The denominator.
exactly. Yes, exactly.
Yes.
We rationalized the numerator in this case. In this case, yeah, that side it was a denominator. This side it's a numerator. So we have got both cases. And the last example that we're doing, we took the we took the numerator. Took the numerator. Okay. So note that you have a number, a plus or a minus sign, and then the radical sign like that. You cannot change the sign here. You cannot say square root of 1 minus x and then you think it will work. It won't. That's the case.
Okay, so say what is this the sign that we show that okay, now we are taking the denominator or now we are taking the numerator. So I will be guiding by what to do that, such a thing.
I am saying if you look at this fraction here, this fraction, you see what separates x and the radical sign is a multiplication sign, not so.
Yeah.
And here either you will have a plus or a minus. So where there is a plus or minus, you have a number, or it can be x. If it is what separates the two, it's a plus or a minus, that's where you change. But where you have multiplication, you cannot do anything.
Or I rationalize where there is a two terms.
Yes, exactly.
Okay. Okay, thanks, sir.
Yeah.
I didn't
Okay.
understand.
Maybe before we end this meeting, some of you are asking about the quiz. It's already 11. Probably it is open. Now you can work on it until say around 3, but you can finish before that. I think that is fair. It is based on the preliminaries, what you already know, what you did in high school necessarily. Yeah, what you did in high school. It's not what we discussed this week. So I wish you all the best. Thank you.
Okay, so say, can I ask?
Mm-hmm.
Yeah, so like, how do we, where do we get, how do we like know, where do we get like this information so we can have the basics of it, the very well, the basics of these questions you were doing.
This class that the lecture we're having.
Yeah, I mean, yeah, the lecture we're having. I mean, where do we like, which pages do we get the resources where like we said like we can get the basics of this so we can be able to master it?
I don't know whether I understand your question, but if you take the study guide that it's on Moodle and you read the first part, you have everything there.
Okay, I think that's what I wanted. Thanks.
Yeah.